Hello everyone. This recording is for fluid mechanics on the 16th of October 2018. So this class meeting is online because I'm down in Clemson, South Carolina working on the FE exam. So let's go over a couple of announcements here. First of all, the homework assignment 4C is due on Tuesday, October 23rd. And one thing I wanted to mention about that set of problems is that for problem 55, you should use a velocity of 5 meters per second. So be sure and make note of that for when you're working on that problem. Now today's recorded lecture is covering some additional information related to Bernoulli's equation, which we began in our most recent class meeting. This recording was put together during a previous semester, so there may be some incidental references to dates or times that may not match up. All of the announcements that are here on this slide right here are the ones that you need to know about for now. So if you have any questions about this material or about the homework assignment, please feel free to stop by my office or send me an email and I'll do my best to respond.
So what I'd like you to do is try and just write down in the margins of your notes here. I've got 4 questions, and if you don't get all 4 right, then you should be very worried. So I consider these extremely easy that you definitely should know at this point. So first question, what kind of acceleration is associated with non-uniform flow? Okay, remember the definition of non-uniform flow, that's where the flow is varying with respect to position. So that's convective acceleration. Okay, so if you got that right, give yourself a bonus point, like if you're keeping track of your own personal bonus points. So at the end of the day, you do something nice for yourself, like, All right, second question. Local acceleration is associated with what kind of flow? Another easy one. You should really beat yourself up if you don't get it. Local acceleration is associated with unsteady flow. So local acceleration is when velocity is changing with respect to time. So unsteady flow means a change in flow conditions with respect to time. I won't ask you to raise your hand if you're 2 for 2 so far, but I can tell by the look on your face that everybody here is still 2 for 2. All right. Okay, third question on this non-quiz quiz. Maybe there's only 3. I thought there was 4 questions. There might just be 3. Anyone so confident that they got it right that they're willing to take a stab at it? Which equation is it that describes the relationship between pressure and local acceleration? It's Euler's equation. Very good. Nice job. Extra personal bonus point, right? I don't give out bonus points, but maybe you do to yourself. All right. Well, good. I hope that you did well on that. By the way, which equation relates pressure changes and convective acceleration? Bernoulli's equation. That's what we're working on today. Let's go back to the example where we left off in class last time, because there's an important idea that I want to re-emphasize in the context of what we're going to be talking about today. So remember this example where we had a nozzle that's contracting an area and that caused the velocity to go up at location 2. But who remembers what was happening to the velocity at location T inside of that stagnation tube? The velocity went to 0. So in other words, the energy along the center line, we're going to assume that the energy is constant. Remember, we've got this magical inviscid fluid where there's never any energy losses. Because it's inviscid, meaning it has no viscosity, that means that it never loses energy due to pipe friction. Now, of course, there's no magical fluid that's completely inviscid, but as long as we apply Bernoulli's equation between 2 points that aren't too far apart, then there's going to be so little energy loss that we don't have to sweat it. Okay, so as the flow is going from 1 to 2, the energy is constant, it's just it's changing form. So we had low velocity here, but high pressure at 1. And then as the velocity increased, some of the energy changed form. So that energy that was existing as a lot of pressure before, some of it went over to additional velocity head. So at 2, there's still the same amount of energy, it just changed form. Now, at the opening of that stagnation point, what we see is that there's a streamline with a dead end. And so there's energy in the form of velocity that suddenly that velocity comes to a halt right at the opening of that stagnation tube. And so what that caused to happen was there was an increase, a localized increase in pressure, because all of the velocity head energy was instantly transformed into additional pressure. All right, so that's just the thing that I want you to keep in the back of your mind, is that when you're intercepting flow, then it causes a localized increase in pressure. We're going through this quiz. Okay, so Bernoulli's equation. It's the relationship that describes acceleration and changes in pressure, where what we're talking about is a local acceleration. I'm sure that some of you have been to like children's museums before, and you've seen like the stream of air going up in like a little ball that somehow floats in the center of that stream of air. So that's one representation that sometimes you can see of the Bernoulli effect. And here's another one. This is an animation that's a flow visualization animation meant to illustrate that the velocity of air over the top of an airfoil, like a wing, is faster. And because you have a faster velocity over the top part of the wing, then that means you have lower pressure, and that's what causes lift, is the differential in pressure between the bottom part of the wing where the pressure is high because you have low velocity, and the top part of the wing where there's low pressure. And so if you multiply that pressure times an area, then that will give you a force. Remember that units of pressure is newtons per meter squared, and wings have area. So you multiply that pressure difference by the area of the wing, and that gives you an idea of the lift force. One thing I'll point out is that the fluid velocity over the top of the wing is faster, but the transit time is not equal. Sometimes, in illustrations similar to this, people will erroneously say that these two streamlines will join back together at the end of the airfoil. They don't. There's a whole lengthy explanation on why that's the case, but the Bernoulli effect is simply the relationship between a change in velocity and a change in pressure. So here's a stagnation tube that's similar to the one that we saw in the example 2 in Thursday's lecture of last week, where we had water flowing along. The last time I think it was a gas. Here it's a liquid. We have a moving river. It's flowing to the right. These blue arrows are indicating the flow is to the right. And we want to look at conditions at 1 and 2. And here 2 is just right at the front face of that stagnation point. And what we know from Bernoulli's equation is that the energy is going to be changing form. And so here's Bernoulli's equation where we've eliminated the elevation term because 1 and 2 are on the same horizontal plane, and so the z's are equal. And this is written in terms of each of the terms of the equation has units of pressure, so pascals or newtons per meter squared. Remember, the other form that we sometimes represent it, each of the terms has units of meters, and that's when we would simply divide by gamma for each one of these terms. But here we're just going to write it in terms of pressure. So what this Bernoulli's equation says is that here at location 1, the fluid is flowing, and there's also some pressure. mostly because of the fact that we're down a certain depth into the fluid. But the pressure also changes as the velocity changes. So we can find the velocity at location 1 by looking at the changes in pressure if we know the velocity at 2 is equal to 0. So between the first term and the second row here, what we've said is that the velocity at 2 is 0 because of that stagnation process where a streamline dead ends. And then inside of this tube, it's static conditions. The reason why the tube has pushed the water up above the free surface that the rest of the water is at, here we can see these little dash marks here that's kind of meant to represent the rippling sheen of water. Well, the water level rose a bit higher inside of that tube that's open to the atmosphere. It's not because there's suction in the tube. This tube is open to the atmosphere, but this rise here, L, is because there's additional pressure at location 2. Additional pressure in the amount of the velocity that was lost. That direct exchange of energy from velocity head to pressure head. So if we approximate the pressure at location 1 as the depth, here D is from the surface down to this horizontal plane multiplied by gamma. So in other words, we're just using the hydrostatic equation to find out what is the pressure at 1. Even though the water is flowing to the right, the hydrostatic equation would give us a pretty good guess of what's the pressure at 1. The pressure at 2, right on the inside of that stagnation point, is going to be more than just related to the depth, because we know it's connected to the stagnation tube, and so if we want to apply the hydrostatic equation, then we would do it between this free surface inside the tube, and we're going to go down through the liquid some distance. The distance that we're going to go down is L plus D. So now we can calculate the pressure at 2 by applying the hydrostatic equation through that stagnation tube. And the velocity at 1, if we just substitute in the term what is the pressure at location 2, what is the pressure at location 1 in terms of the depths, and then we combine those terms, then it turns out that the velocity is easy enough to calculate. It's just the square root of 2gl, where L is that additional distance above the water surface that the water is rising because of the stagnation, where that stop of the velocity, all of the energy that existed as velocity before, is causing the water to rise up inside of the tube. Now this only works as long as the opening is pointed at the flow itself, right? If this tube terminated, I wish I could write on the screen. Let me do it this way. What if the tube looked like this? And here's the opening. It's pointing down. And the flow is still just coming. Oh, Jesus. That's the best arrow I can draw, guys. All right. So the flow is still going this way. There's not going to be any rise in the water if the opening of the stagnation tube is just pointed down. It has to be pointed so that these streamlines dead end at the opening. Yeah?
What if it's at an angle?
Then it would be somewhere in between, right? If it's at a 45-degree angle maybe, right? Then maybe what we'd want to find out is what is the actual area that's intercepting the flow compared to the area of the tube. So, but it would be somewhere in between. Great question. Yeah. So you're saying, what if it was like this, right? And the flow's going around it. Probably it would, but we don't have the same way to say that all of the energy is dead ending, because the flow is going to be going around that opening and then it's going to be going around it again. So I think there probably would be some suction, but I don't think that if it was pointed the other way, I don't think it would suck it down in the same L distance. That would be a great, like, senior project kind of a research thing, though. develop an illustration for outreach or something. Other questions related to the stagnation tube? All right. So the next level, taking a stagnation tube to maybe a more sophisticated place that is more broadly applicable out in the field, is a Pitot tube. Now the weakness with the stagnation tube is that this device really only works if you're measuring the flow of a liquid. And remember that we have to have some tube sticking out of the liquid so that we can measure the L. So it's not that it's useless, but it could be made more useful. And we want to get around the disadvantages of the stagnation tube with this Pitot tube. So the Pitot tube, number one, it can be used in liquids and gases. So it's not as limited in that way. And the other thing that's kind of nice is it's measuring a difference in pressure. Rather than measuring some height of a liquid rising inside of a tube, we can just connect a gauge now and measure a difference in pressure. But let's talk about why the difference in pressure arises. Let's assume just for now that this is a top view of the Pitot tube, that we're looking down from above on the Pitot tube. And the reason why I say that is it's easier if 1 and 2 are at the same elevation. Just for our first look at what the Pitot tube is doing. So you'll notice again that we have some fluid that is moving in a certain direction towards this Pitot tube. Doesn't matter if it's a liquid or a gas, the Pitot tube can measure either. But some of the liquid is going to be encountering this open end of the Pitot tube, and so if we follow this central open end, we'll notice that this is like a maze that you'd get on the menu at Denny's. I'm almost there. I want to make it, guys. All right, the stagnation pressure tap. So that's where the pressure is going to be higher than in the static pressure tap. So the static pressure tap, if we follow the maze the other way out, almost there. Eureka. All right. So look at how these two locations are different. Location 1 and location 2. How do they encounter the flow? They're both going to experience the overall ambient pressure of the fluid, but location 1 has got some additional pressure it's going to be registering because it's intercepting the streamlines of the fluid. And so the fluid just goes around location 2. You know, that opening at location 2 isn't intercepting any streamlines, but here at 1 it is. And so that same idea that we had before in the stagnation tap, that there's some little extra amount that's causing the pressure to increase because the energy is transforming from its velocity head to additional pressure head, that's happening at 1. But at 2, there isn't the velocity head exchanging into pressure head. So let's apply Bernoulli's equation and look at what that says about this Pitot tube. We've got location 1, location 2. We're assuming that they're on the same elevation plane, so we'll cancel out the z's. And then what that means is we can assume that the pressure at, the velocity at 1 is 0. So we've canceled that out here. And you'll notice here that we're going to measure the difference in piezometric pressure between 1 and 2. Now, piezometric pressure is just P plus gamma Z when we are in terms of wanting to know both the change in pressure and the change in elevation. So P sub Z is pressure plus gamma Z. All right. So if 1 and 2 are the same elevation, then P sub Z1 minus P sub Z2 really is just delta P. And so that's exactly what this is measuring with this instrument connected to the end of the Pitot tube. You can measure the change in pressure, and as long as you know the density of the gas or liquid, so the density of the fluid that's being encountered, then you can find the velocity of the fluid here at location 2. So it's a very useful device there for example, found on aircraft, and it translates a change in pressure in the instrument panel into the wind speed that the plane is encountering. So let's say that we have a pressure gauge like this connected to a pitot tube, but the pressure gauge, look at this one. I don't know if those of you in the back can necessarily see it, but this gauge, just the image I found online, went from 0 to 4 bar. So the maximum pressure differential on this picture is 4 bar. Let's say that we have another gauge and the maximum differential, it'll go from 0 to 7.5 kilopascals. What if you were asked to design a pitot tube / pressure gauge device, and you wanted to know, well, with this gauge, what kind of maximum airspeed would you be able to measure? You know, is it appropriate for a Cessna, like is pictured here, that we have a rough idea of what its maximum speed is going to be? So in this example, what I'd like you to do is apply the ideas of Bernoulli's equation. Now here I've turned the pitot tube on its side just to help you kind of see that, you know, here's the pitot tube in the picture, here's the pitot tube concept that we've got, and you can almost see it that there's an opening in the front and an opening on the side. So it's measuring those two different pressures. The one on the side doesn't have the extra pressure due to the velocity ending. A typical density of air would be 1.2 kilograms per cubic meter. So try and translate that into a maximum airspeed if we had the pressure difference being up to 7.5 kilopascals. All right, so we've got Bernoulli's equation that applies between location 1 and location 2. And what it's going to help us to know is that change in velocity between the two locations, how much change in pressure we should see. Now, we're given a change in pressure, and so what that's going to, you know, if we substitute in the difference in pressure, what that's going to allow us to solve for then is the unknown velocity at 2. The velocity at 1 is 0. Now, by location 2, what we should say is that's just on the outside of that opening. It's not actually, that's not the velocity inside the pitot tube. So maybe I drew my drawing a little bit sloppy, because if you look where I put that dot, I said location 2 is on the inside of the pitot tube. I was wrong, dead wrong. So a better location for it would be just on the outside, because inside the pitot tube conditions are static. There's actually no movement of fluid inside the pitot tube. So just on the outside of the pitot tube is the passing by wind speed that we're trying to calculate. So I'll adjust that drawing. What it ends up being is about 400 kilometers per hour. So that should be plenty for a Cessna. They don't go that fast. Any questions on this example? All right. Well, let's take things to the next level. And the way we do that is by combining two ideas together. Here is combining the idea of a pitot tube, which is all about Bernoulli's equation. And then we also have a differential manometer. So we're going to have part of this problem being like our manometer equation, and then the manometer equation expression we come up with, we're going to substitute into the pitot tube expression. Now, we've done a similar example to this before, where we started at one point in the manometer and we worked our way through the manometer to find the pressure at 1 in terms of the pressure at 2. You may remember it was the sort of thing where we said, you know, just to begin with, pressure at 1 plus, and Now we're working at 1 on the inside of the pitot tube and then through the rest of the manometer. We're going down some distance through some fluid. Now here the two fluids are kerosene, which is flowing through the pipe, and then this bluish fluid here, it looks like, is mercury, which is far more dense. Okay, so we have some pressure at 1 plus the gamma of kerosene. Z1 minus Z2 is the distance that we're going down. And then we're still continuing to go down through kerosene, some distance L. So it's plus gamma of kerosene times L. And I'd like you to do the rest of it. So there's more and more and more, and then eventually that gets us to P2. All of that is equal to P2, just applying the hydrostatic equation through the manometer. And then once you get that manometer equation written, okay, we'll have a manometer equation. Once you get it written, rearrange everything. So you're doing your algebra rearrangement so that we have P sub Z1 minus P sub Z2 is equal to what? And remember, P sub Z, what we mean by P sub Z is pressure plus gamma Z. So if we're saying P sub Z1, that means P1 plus gamma Z1. P sub Z2 is P2 plus gamma Z2. So in the manometer equation, finish writing it in, then do the algebra 3-card Monty, switching things all over the place until you've got on the left-hand side the change in piezometric pressure, and on the right-hand side is everything else. And the reason why we want that in the manometer equation is that then here is our pitot tube equation. You know, if we rearrange Bernoulli's equation with the assumption that the velocity at location 1 is 0, because that's what happens inside of a pitot tube, this is what we get. So you'll notice inside the interior of the pitot tube equation is P sub Z1 minus P sub Z2. Well, that should sound familiar because over here in the manometer equation, you just rearranged the manometer equation to find what is P sub Z1 minus P sub Z2. In other words, what we're doing is we're using the manometer to find the difference in piezometric pressure between the 2 points. And rather than using this gauge, we're using a different type of gauge. We're using a manometer instead of a direct pressure gauge. All right, so I've given you a couple hints. I'm going to give you a few moments to fill in the rest of the blanks there, and we'll regroup and see what you get as the velocity at 2. What we're trying to find out is if you've got 18 centimeters of deflection, then what does that mean about the velocity of kerosene through the pipe? There we go. Okay, so we've just actually reproved to ourselves something that I think if you went back through your notes, you would see that we've already said delta P sub Z in a manometer is the difference in the unit weights multiplied by the deflection. So what we're saying is this manometer, it doesn't just measure pressure, it measures the difference in piezometric pressure between 2 points. And that's important because in this tube of kerosene between 1 and 2, the pressure, of course the pressure is going to be different between 1 and 2, partly because of the hydrostatic equation. You know, 2 is lower down in the fluid, and so the pressure change is partly due to that. Well, this manometer is measuring not just the change in pressure, but it's measuring the change in piezometric pressure. So it's keeping track of the elevation, and so it's measuring the change in pressure relative to the elevation difference. And so that's a useful thing for our case, because once we have the manometer equation and go through canceling out all the terms and distributing the gamma k times the elevation so that we can do the grouping. So P sub z1 minus P sub z2 on the left-hand side. On the right-hand side, it's the deflection times the difference in the unit weights. So then we can substitute that into the pitot tube equation that we previously derived from what? Bernoulli's equation, assuming that the velocity at 1 is 0. Okay? And the gamma, I got a good question. You know, the density. What density should you use here in the pitot tube equation? It should be the density of the fluid that's being measured. And so we're measuring kerosene. That's what's flowing on the outside. So really, we've got an inside equation and the outside equation. On the inside of the pitot tube, conditions were static. And that's why over here on the board, the manometer equation was just the hydrostatic equation between 2 points. So we were relating 1 and 2 through the inside of the network using hydrostatic equation, and then we were saying the difference in pressure or velocity between 1 and 2 on the outside of the pitot tube, that's described by Bernoulli's equation. And so here, when we had Bernoulli's equation rearranged with the assumption that the velocity at 1 is 0, then that's the pitot tube equation, and we'll just drop in the y deflection of 18 centimeters and the difference in the unit weights and the density of the kerosene. And so I hope what you got on this one was that the velocity at 2 is 7.47 meters per second. So this is just an easy way, relatively easy, of measuring the flow rate through the pipe. Because if we know the velocity, then we'd simply know, we'd multiply the cross-sectional area by that velocity, and that would turn it into a volumetric flow rate. Okay, do you have questions about that example? Let's look at a homework problem. All right, so problem 51. We have a venturi. And this is what we're going to look at in the lab today and tomorrow, is a venturi. And in a venturi, it's a pipe where the diameter constricts so that the velocity goes up, and then the diameter goes back to normal again. So it's just sort of a temporary restriction in the throat of a pipe, and that temporary constriction increases the velocity and decreases the pressure. And so how do we know the pressure is lower? If you look at these two stagnation tubes here, these two piezometers, you'll notice that the elevation is higher at this lower location than it is at the upper location. So if we're comparing 1 and 2, we can tell just by looking that the pressure at 2 is higher than the pressure at 1 in the amount of 6 inches of whatever this fluid is. So it's Bernoulli's equation that we can use to apply to find the relationship between pressure change and velocity change. And so here 10 is the V1, V2 is unknown. We don't know the actual pressures at 1 and 2, but we do know the difference in pressure, which is good enough because we can rearrange this Bernoulli's equation in terms of a difference in pressure. So if you rearrange it to group the terms by piezometric pressure like we just did in the example, then you can use the 6-inch deflection to find what the velocity is at location 2. So I hope that this problem should be relatively simple now that we worked through that Pitot example, which is very closely related.